My name is Dr. Shobbusha Chishen. I am the Dean Research and Development of GIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bokeh is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you will be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we will be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Hello students, how are you? Very good morning to all of you. It has been a fun journey so far with quantum mechanics too. And every day, as I normally do, I'll remind you the basics of quantum mechanics too. And in fact, in my previous class of quantum mechanics too, what I did, I have made a summary of everything that I have taught you, okay, over the past 9 classes now. This is going to be the 10th class in a row. Quantum mechanics 2 is a part of your physics 2 courses, okay, whose 50% is quantum mechanics, where you're talking about microscopic particle like electron. Its behavior, you cannot do anything. Any part of the mechanics of electron could not be done directly. So entire process electron to us is a mathematical function psi. So entire process of quantum mechanics is a mathematical process. We are using mathematics to describe the wave nature of the matter electron, that is the function psi. So as I usually do, I will be again reminding you now. Possibly today is the last time. Okay, I will be making the recapitulation because next class onwards, okay, we will be talking about the direct solution of the problem. There you have to remember, okay, the basics of the idea. I hope you can remember. It is not going to be difficult for you. That simple mantra in a quantum mechanics class, we talk about these issues. We talk about the, this is me, you know it, and we talk about the wavy nature of the matter. Four things can happen in nature. Matters can be metal-like collision. Okay, they can fight, they can collide. Waves can be waves-like superposition. Wave can be wave can be metal-like photonic nature or phononic nature. And material and a wave nature of the matter. There is a fourth aspect you are talking about is the pedagogy of the class. That has been that the idea of Louis de Broglie initially, and we are now trying to prove that through that has been proved through Davisson-Germer experiment, you know. And this wave nature of the matter is this much. Matter electron is our main area of concern. Okay, electron is the most important person in our quantum mechanics class. Everything we are talking about is dynamics of electron mainly. So in our class, we are following this green line, wavy nature of the matter electron. Wavy nature of the matter electron is manifested by a mathematical function psi with psi square, giving you the probability of finding the particle, total probability. One, this thing you know. In a problem, you can calculate psi by solving the equation of Schrodinger that you also know. Okay, this is the most important equation. Next day onwards, we will solve Schrodinger equation. Okay. It's very important, solution of Schrodinger equation. So now after that, what shall I do? In this equation, just to remind you, the potential energy V term is the key. From problem to problem, we will be solving problem from next class onwards. There are 3 problems in your course. One of them usually comes in examination. So be very careful when you solve problem and don't miss those portions, okay? So now Schrodinger equation will give you psi, but after getting psi, you have got many jobs to do, okay? So suppose electrons are moving, okay, you see psi is like that, okay, that is a wave function of the electron as you can see on the screen, okay, that is a wave function of the electron, and these wave functions are will be actually developing the entire mechanics. It's like a small capsule. It's just a mathematical formula, but the power of mathematics is so tremendous that it will develop the entire mechanics, entire mechanical world, the description of motion, knowing its position at a given time, velocity, momentum, kinetic energy, potential energy, everything that we can generate out of this simple function psi. How do you generate that? By using the common sense of mathematics. Psi is a function. You talk with psi, you interact with psi in the language of mathematical operators. So anything you wish to measure, you know, this data table, that there for every operation, anything you do, anything you do in quantum mechanics, you have to interact with psi in the language of operators. Okay, so these are the mathematical operators. Their job is to interact with psi and giving you physical data. So this is the list of variables you wish to measure, and for every variable you can see there exists a mathematical operator. Okay, the symbol of representation is that you use the classical symbol with a cap, makes a quantum operator, and I requested you to remember the operator form of position and time is unchanged, and momentum is you have to remember the operator form, which is space differentiation operator in 1D. For one-dimensional x directional motion, it is del L x, in front of that there is a minus I cut. If the water was moving in y direction, it should have been del L y. So it's a first order derivative in space. If it was moving in z, del L z, and if it is moving in 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 free space for that matter, so it will del L r kind of thing. Okay. So basically, if you take the p square by 2m, or if you put the operator form, you will get kinetic energy, which is double differentiation operator. V does not change, it's a function of x, so it is also unchanged because x is not changing and Hamiltonian is there.
and potential time energy any energy is I plus h cut del del t. Now these operators are going to help you to generate any information of motion, because operators are the question you are asking to psi. So if you have to get momentum on the given wave function, say for example e to the power ikx or sine function, you operate the corresponding operator. If you have to get momentum t electron psi, if you have to get kinetic energy t electron psi, and if after operation you satisfy an eigenvalue equation means operator will act on the function and return the function back, that is called an eigenvalue equation. Then the constant on the right hand side, in this case of momentum, in this case in this picture, uh, the momentum is basically replicating the value of the kinetic, that h p psi 1 is equal to h cut k. H cut means h by 2 pi. H cut k psi, you see psi 1 back e to the power function back, that is an eigenvalue equation with h cut k is a momentum value. I told you it is a structure. In a problem you have to put the correct value of h cut and k to get the actual value of the momentum. So kinetic energy is similarly h cut square k square by 2m. So in a problem you have to put the correct value of k and m and h cut to get the value of the kinetic energy. So this is the superposition principle. So that allowed states, mixed states are also allowed. And this is orthogonality idea, okay, that the conjugate of a function and its function on integration gives you 0, with that two dissimilar function and same function and its conjugate will give you 1. So this thing you know, and these are the basic, so same function and its conjugate will going to give you 1, and otherwise two dissimilar function will give you 0. It makes your mathematical life very simple. Only sine, only cos, that means one function is 1, another function is sine or cos, x sine x, x square cos x. So these are all going to be 0, sine and cos together. And if you've got sine square, cos square, that means same function and its conjugate, then you'll get non-zero result, ideally 1. So ultimately you get normalization condition also. And the concept of, so what you have been doing, you have been using the mathematics idea, for example, eigenvalue equation to do measurement. Another mathematical idea is the commutator bracket. It's a mathematical idea that this is a commutator bracket condition formula of any two operator A and B, AB minus BA. So if they commute, that means if it is 0, they commute, then they can measure those variables together in an experiment. If they don't commute, you cannot measure them together in an experiment. Okay. So just like position and momentum don't commute, kinetic energy, potential, they do commute. Energy and time don't commute. All these things you can see. Because x and d to dx means position and kinetic energy commute. So basically in this way, just by applying the basic ideas of mathematics, we can interpret physics result, because we are helpless here. We have to do everything mathematically. So mathematics prescription is the prescription of us. Basically, we have to rely on that. The results of mathematics we are utilizing. So now after that, from one particle to, we have moved to many particle case, particularly last day. So I've got many electrons moving together. So you see that is the first is one particle case. Okay. It's a beautiful picture. One particle's position and momentum as told by connected by uncertainty principle. Now if I've got many electrons moving together, so then how do you describe that problem? Okay, because I have to describe all the electrons are all similar. Okay, how do I describe, how together I can define their position, how together I can define their momentum or kinetic energy or potential energy? That is the focal point now. Now that answer is that if you have got, now we are moving from one object to many objects. Most of the problem initially we do it about eigenvalue equation, calculation, commutator bracket are all about whether you can measure a particular variable, kinetic energy or momentum of particular electron, one electron. If you measure, can you measure more than one data together, like kinetic energy and position, or position and momentum? So some cases we can, some cases we cannot, as prescribed by a commutator bracket relation. Now we have never discussed as in general about the many particle case. So that is something. So we discussed last day, but before last day actually we have never discussed. So I presented it in this way. Many particles. I told about large object. Okay, suppose I've got many colored balls are there. There are many objects, but so that is also a many particle system. The below one is also a many particle system. These are all the red balls. So if you have to describe that motion, you see, for many particles moving, suppose I have got 4 different colored ball: red ball, green ball, blue ball, and yellow ball. So you can describe, your advantage is that they are all dissimilar objects. They are all balls identical but distinguishable. So you can separately say where blue is there, it may be x1. Where red is there, it may be x2. Where green is there, x3. Where orange is there, x4. So you can specifically mention where individual balls are there. So you can specifically separately describe their journey. So life is easy. Even it's a many particle case, but it's a many identical and distinguishable objects. You can describe them. Problem actually begins if you have got this case. Many dissimilar objects are there, identical objects but indistinguishable. All are red balls. All of them are red balls. So if I have to describe that position, which one is ball number 1, which one is ball number 4, I do not know. Here I could be specific. Which one is orange, which one is red, which one is blue, which one is green, I can see, I can realize, because these are big objects, macroscopic objects, so you can see the balls. Second, I can identify the balls. So identify each ball, that means how each ball is moving, I can describe. So it is basically, although many particle case, but it is summation of many single particle case basically. Problem actually becomes when we describe many similar objects, then you cannot distinguish. Even if you change their position also, you cannot understand. So what you do in this case, your life is, you're dealing with many dissimilar objects, many identical objects, all are balls but indistinguishable objects. So your technique will be something different here. You have to say on an average they are between x1 to x4. Okay, this is the average value concept of classical physics. Quantum mechanics is different. Quantum mechanics is that you are not dealing with balls there. You cannot see the balls at all. You cannot see the matter. So that x1 and x4 you cannot do directly. You have to get it from psi. Okay, so that is the technique I told you. How do you get it from the wave function? Okay, this is the formula of getting any operator's average value. I request you to remember the orthogonality condition for same function, because all are identical particle, all of them are having same psi. Write down it twice in the numerator and denominator, and in the numerator you put the, in between x psi and psi, you put the operator. So denominator becomes 1 for normalized function. So ultimately this becomes the actual formula of, on most of the occasion for normalized wave function, this will be the formula of getting the average value. And last day, in fact, we solved some problems also. These are the problems we did. A by 2 was the position like that. Now after that, I made a summary of the entire discussion. Even today also I mentioned that entire summary. That herein we only talk about psi is the most important parameter, the wave function that is replicating the matter. The dynamical variables are represented as operators. Any operators is measurable if it satisfies the eigenvalue equation, and that is a formula of average value. But most important issue that I never discussed is that suppose I solve Schrodinger equation, I get a psi. Can any solution of Schrodinger equation will represent the matter? Last day before I left your video lecture, at the end of the discussion, I told you that any given psi has to satisfy some condition, just to be an accept well-behaved function. And in mathematics, well-behaved, this is not our human well-behavior, okay? It is a mathematical well-behavior. In mathematics, a function is called well-behaved if it is single-valued, because it is representing a matter electron. It should have only one value, one electron at one value at a given point of time. Okay, it is finite because it is representing a matter. Matters are finite body. If it is analytic. Analytic means single-valued and first and second derivative will exist. That means the continuity condition, same matter is moving. So if these things are obeyed, suppose I solve Schrodinger equation, if these three qualities are obeyed, or if the negative approach, if one of the qualities is not obeyed, then it is not acceptable. That is the message. Okay, that is the mantra. So now this problem will come up, because now our next job is to solve actual problem of quantum mechanics. So it will come up very soon. So we'll see that, we'll understand that, we'll discuss that. So but before that, what shall I do now? I'll show you and real life two types of problem actually comes in examination. It makes mostly as MCQ. Some psis are given, will be asked which one is going to represent a matter or not. This is very easy, take it from me. And you know, these all 5 points together are called postulates of quantum mechanics. So in examination from the last postulate, MCQs are 2 marks question from the commutator bracket calculation or acceptability of wave function, that is, or eigenvalue calculation, all these things. And this might also come as a separate question. Write down postulates of quantum mechanics. Okay, they are very simple and illustrated well to you. So now let me show you some real problem. Okay, how you anticipate measure a acceptable wave function. Two way it comes in. Either, okay, as a functions are given, you see so many functions are there, or you'll be asked to either graphically given or by formula it is given. Let me show you. Please realize it. Now the first point is that, so acceptability of wave function we are talking about. So psi will be given, and it should have three qualities as I mentioned. The wave function has to be finite, wave function has to be single valued, wave function has to be analytic. If one of the condition is not waived, then it is not acceptable. So you have to check it. The one type of question that comes in examination is this much. Suppose one question is this much. Suppose some figures are given. Suppose this is one wave function. This is psi versus x plot. Suppose this is another psi. Suppose this is another psi. And here is another psi. So four psis I have given in front of you. So I have to judge which one is acceptable or not. So how do you judge it? First, let me change. So we'll mainly focus on these two issues, finiteness and single valuedness. If one of them is not accepted, then it is gone. I choose a point x1 here. At a point x1, how many values psi has? It has got three values. So it has got three values. So it is not a single valued function. So if I choose any other point x2, how many values psi has? It has got three values. So it is not a single valued function. So it is not acceptable. Not acceptable. So it is not a single valued function. So not acceptable. Now come to the next case. If I choose again 2 points, x1, at x1 how many values psi has? 1. At x2 how many values psi has? 1. So it has got, at a given point psi has got only one value. So it is single valued. So it is single valued already. But problem is that you see this function is not ending. Okay, it's a continuous function. It is not closed function. So it is not finite. It is continuing. So obviously it is not acceptable. So both, one of the criteria is not acceptable. Same problem here also. If I choose 2 points x1 and x2, at x1 and x2 you see, if you look at your psi, it is single valued. And but problem is that this is not a closed loop. It is not a closed loop. It is not finite. So also not acceptable. Now come to the last case. I choose 2 points x1 and x2. At x1 how many values psi has? Only one value. At x2 how many psi has value? Psi has only one value. So these are single valued. Problem is that this, and if I look at the finiteness, it is finite also. And you see this is nothing but a sine function, and we have been taking sine function so many times as an example of acceptable wave function. We calculated expectation value, many things. Okay, the calculation of the normalization condition application. So this is obviously the acceptable wave function. So just to satisfy both the criteria. So this is one type of problem. Another type of problem that might come in examination is that here I have given the graphs. So instead of giving graphs, you may be given directly some formula. So this is second nature of the problem. Suppose you are given some formula. Suppose psi x is given as a e to the power ax. This is one psi. Another psi is given as a e to the power minus x. Another psi is given as 1 by 1 plus x. And another psi is given as a e to the power minus ax square. These are the four psis. So suppose this is psi 1, psi 2, psi 3 and psi 4. Which one is acceptable? Again, my mantra is that the wave function psi has to be finite. It has to be single valued and also analytic. If it is not satisfying one of the criteria, then it is gone. So let me judge it. So let me first do it. So idea is that I will mainly focus on this one, finiteness, because I have not plotted yet. So if I have to just, finiteness means you have to check whether there exists any x value where it can become infinite. Suppose x is plus infinity. So psi 1 will be a to the power infinity, going to infinity. And x goes to minus infinity. Psi 1 will be a to the power minus infinity, going to 0. 0 is acceptable. Suppose x is going to 0, the psi 1 will be a, because e to the power 0 is 1. But you see, problem is that it is becoming infinite for a some value of x. If it is becoming infinite for any x value, it is not acceptable. Actually, this function is nothing but an exponentially growing function. Okay, and it is single valued, you can see here, but not finite. Come to the next case. If we do the same thing at x goes to plus infinity, psi 2 will become a to the power minus infinity, going to 0. So okay, 0 is acceptable. Our problem is that as x goes to minus infinity, psi 2 is a to the power infinity. So going to infinity, so again problem is there. And at x is goes to 0, psi 2 is equal to a. A is okay. But problem is that it is becoming infinite as x goes to minus infinity. So it is not acceptable. And you know, this graph is nothing but this graph. Okay, this is an exponentially, it is a curve like this. Now come to the last case. At x goes to plus infinity is 1 by 1 plus infinity, going to 0. Minus infinity, 1 by 1 minus infinity, going to 0. So 0, 0, okay. At x goes to 0, this is 1 by 1 plus 0, 1. So it is also okay. So is it acceptable? Question is that, point is that it has to be acceptable for all x. It will be having problem at x equal to minus 1. 1 minus 1 means it is going to diverge. So if it is becoming infinite for any value of x, it is not acceptable. So again, the last one is our only hope. So again, now let us judge it. At x goes to plus infinity, psi 4 will become a e to the power minus infinity, so it goes to 0. X goes to minus infinity, a e to the power minus of a minus infinity square. So a e to the power minus square plus a to the power infinity goes to 0. As x goes to 0, psi 4 is a. So you see, it is all everywhere, it is finite. So it is okay, it is acceptable. So this is the last option. Now if I plot it in a graph, this graph, the last one, if I show it separately, that is psi 4 is equal to a to the power minus ax square. As you can see, this becomes 0 as x goes to plus infinity. This becomes 0 as x goes to minus infinity. And this becomes a as again s goes to 0, x equal to 0. So if I plot it in a graph, at x equal to 0, it is a. At x goes to plus infinity, it is going to be 0. X goes to minus infinity, it is going to be 0. So if you plot it, the graph would be like this much. It's a very typical graph. You might have seen it. This is called a Gaussian curve. This is called a Gaussian curve. Some people call it normal distribution function. This is called normal distribution function. And this is an acceptable, and this is actually a closed curve. You can see here, this is finite and this is single valued. So basically at a given value of x, it has got only one value. Okay, this is basically a bound function. So many qualities it has, so it is acceptable. Okay, Now actually this type of structure in examination, this any structure like this, okay, may be given, and that is representing the Gaussian function and acceptable wave function. Sometimes it is given, suppose you are given a is equal to only minus x square. So that means you are choosing a equal to 1. Suppose this is the a equal to 1 graph. Now suppose it might happen a greater than 1. A greater than 1 means key. If you look at this formula, because of the minus sign it is falling. So a greater than 1 means that will refer to a case of quick fall. This is the case of a greater than 1. And sometime it might happen a is less than 1. So if you look at this expression, here it is representing a slow fall. So slow fall means it will be falling a bit slowly. It will go to follow this curve, but this curve will be like this. It will be falling a bit slowly. Okay, this is maybe for a less than 1. Okay, but greater than 0. Okay, so this is called normal distribution function also. So this is the way we talk about acceptability of a function. So I made a thorough and smooth journey about the whether any wave function is acceptable or not. Mind it, mantra is that you have to first check the finiteness. If it is finite, then it is acceptable. Okay. Now let me just get back to the PPT part again. Okay, you can see so many wave functions I have plotted here. These will be coming here. Okay, these are all sinusoidal function acceptable. Okay, we have already studied with example. So our the conclusion is that we can explain the acceptability of a function. Examination, these 8 cases I have shown you, they normally comes as a MCQ question. Okay, I hope you can answer. You have to judge 2 things: finiteness, single valuedness. Mainly finiteness is the key in most of the cases. Okay, and Gaussian functions, sinusoidal functions are acceptable function. Okay, so that's all fair. Okay, so now what shall I do now? Bye for the time being. We'll come up with the solution of actual problem, actual application of Schrodinger equation in the next video lecture. Thank you.